Hi, I'm Nathaniel.
Hi, I'm Tamanna.
Welcome to Design of Machine Element Bearing Lab.
The objectives for Bearing Lab are to become familiar with the different types of bearings used in machine systems, to gain experience selecting an appropriate bearing to use for a specific application, to gain experience looking up bearings in manufacturers' online bearing catalogs.
Today we will cover 4 stations to categorize bearing types, apply proper design criterion, and identify their use within machine systems. Bearings are rolling machine elements which constrain motion and reduce friction between moving, often rotating parts. Bearings consist of 4 main parts: an outer raceway, an inner raceway, bearings which roll between the inner and outer raceway, and a cage which keeps all the bearings in place. By reducing friction, bearings quiet machine operation and increase the efficiency of machine systems. Bearings are often produced in 2 principal types, spherical and cylindrical. Bearings are often made from wire stock formed into the desired shape through rough press and fine grinding operations. A final heat treatment means that good bearings are both hard and brittle.
One of the most commonly used rolling bearings is the ball bearing. Ball bearings are designed to handle both radial and thrust loads. There are different types of ball bearings, including deep groove, shielded, sealed, etc. Ball bearings are relatively inexpensive compared to other bearings and are commonly used in applications where the loads are relatively small. In a ball bearing, the load is transmitted from the outer race to the ball and from the ball to the inner race. The ball is a sphere that makes contact with the inner and outer races by point contact. Because of this point contact, a ball bearing can be ruined if it is improperly overloaded. A straight roller bearing utilizes a cylinder instead of a ball as the roller. The contact with the inner and outer races in a straight roller bearing is a line rather than a point. Thus, it can handle larger radial loads than a ball bearing. Straight roller bearings are not designed to handle thrust loads. They require almost perfect geometry of the raceways and rollers. A slight misalignment causes the rollers to skew and thus may ruin the bearing. A tapered roller bearing is designed to handle both radial and thrust loads. These bearings are available in single, double, and 4-row designs depending on the requirements of the application. They utilize tapered rollers that are oriented at an angle to support the thrust loads. Tapered roller bearings are used where radial and thrust loads are present. Spherical roller bearings are used to handle high radial loads and are designed to adjust to misalignment of rotating components. They are used in applications such as gear drives and continuous casters. A thrust bearing is designed to support a thrust or axial load. 2 common types of thrust bearings include ball thrust bearings and roller thrust bearings. In ball thrust bearings, the rolling elements are balls. They are used for low-speed applications where the radial load is small. Ball roller bearings cannot handle large radial loads and are not used in applications where radial loads are present. Roller thrust bearings use cylindrical rollers and can support large thrust loads.
When mounting bearings onto shafts, care should be taken not to misalign the spheres or cylindrical rollers within, as this can damage the bearing, decreasing performance and lifespan. To mate bearings to shafts, special tools which apply force to a bearing's raceway are typically used. When designing machines which require bearings, engineers will often create shafts with stepped profiles to ease bearing assembly. For increased holding power, bearings can be heated and cooled to clamp onto a shaft. Now, as good as bearings are at reducing friction, know that there is no substitute for a good lubricant like grease or oil. With that brief overview of bearings, let's run over to Station 1.
So this is bearing number 1. And here's the back part. Now I will show you bearing number 2. So now I can move from the outer raceway, and this is the bearing, and this is the cage, and this is the inner raceway. Now this is bearing number 3. So this I can show you disassembling the outer raceway too. And this is the bearing. This is bearing number 4. Now I'll show you bearing number 5. So here you can see that the bearings are covered by rubber materials, but still you can spin like this, okay? Now this is bearing number 6, and here you can see that the bearings are covered by metal material, and also you can spin like this. And this is bearing number 7, and you can see the bearing inside, and note that there is no inner race in the bearing. And now this is bearing number 8. Here you can see that the bearing inside, and this is within the covered case, so you can add in grease to lubricate the bearing.
Thanks for tuning in to Station 2. What marvelous things are bearings? Bearings help keep the world happy and spinning.
But what happens, and how will you know when bearings go bad?
I'm pretty sure you can hear it, so that's what that is. It's pretty freaking loud.
I'm trying to separate the bearing like if we're shaking the tire, but there's no movement here, it's solid. But it feels gritty, it doesn't feel smooth. And let me put this up to the mic so you can hear it.
Now it's time to play Good or Bad Bearing!
And now for something completely different.
Now, most bearings do not start off as bad bearings. Most, in fact, are good and well designed to start with. However, by subjecting a bearing to an excessive load, running the bearing faster or longer than necessary, the bearing will degrade quickly. A good designer must keep in mind the principles with which to select a bearing, balancing performance requirements without breaking the bank. In bearing design, it is well understood that there is a constant relation between bearing life and load placed on a bearing. This means that for both spherical and cylindrical bearings, we can design a desired bearing based off of a manufacturer's rating, as both the desired and rated relations are equal to the same constant. Often, manufacturers rate a bearing after 1,000,000 revolutions, hence the simplified formula in Norton's book. But this may not always be the case, so I will leave the equation in the unsimplified form. Now, while a manufacturer may rate a single bearing, not every bearing which comes off of the assembly line is identical. To account for this, a Weibull distribution of failure is commonly employed. A list of reliability factors with common Weibull parameters are given by Norton, but I have provided an expanded formula. A final note to mention is that bearings commonly exist in pairs. Therefore, one should remember the laws of probability and reliability. This leads to a final equation given here. So, let's do an example. Let's say we are to design a helical gear and wish to place a pair of bearings on the shaft. The operational conditions are also given. From this big picture, we can discombobulate the problem into a few simpler free body diagrams. From this, we find reaction forces at locations A and B and their resultants. Let's say that our company has an exclusive deal from Timken to provide the bearings. Timken provides several parameters relevant to their roller bearings, which include values for X and V in our equivalent load equation. However, the Y value, known as the thrust factor, changes depending on which bearing one chooses. The thrust vectors can vary quite a bit, but a value of 1.5 is generally a fair first guess. This also allows us to find an equivalent thrust load on the bearings. From this information, we can find our equivalent loads on bearings A and B. These values can be inserted into our equations for dynamic and rated loads. Note that Timken rates their bearings after 90 million revolutions rather than a single million, and our problem statements requests an application factor of 1. I've included the application factor into the equation in red. Timken also provides specific values for the Weibull distribution, which we will employ here. The reliability for the machine system is required to meet or exceed 0.99. We shall assume here that we will choose identical bearings in the design based on the largest load. Therefore, we require a 0.995 reliability for a single bearing. Solving for the desired catalog rating with an application factor shown in red of 1, we find the required bearing pair which can meet or exceed the 11.5 kilonewton and 6.5 kilonewton load requirements. Let us choose the cup and cone pair for both bearings based on the largest force requirement. Going through this quick reference sheet, we find a possible bearing. It looks like part number 15100 and 15245. Let's double check that. See if we can still find it in stock. Going online here, we go to Timken's website. We look for some engineering help. And they see that Timken provides a helpful bearing life selector and bearing life calculator. Given these tools, please answer the remaining questions within the lab before heading on to Station 4.
Now this is Rexnord gearbox, and here this is gear, and here you can see the bearing. Now please answer all the questions on Rexnord gearbox. Now I will show you the Harley-Davidson transmission. Here you can see the bearing, and now I will show you the gear along the shaft. Now please answer all the questions on Harley-Davidson transmission. Now this is right angle gearbox. Here you can see the gear. Now I will show a closer view of the bearing. Here, this is the bearing. Now please answer all the questions on right angle gearbox.
Thank you for joining us for Bearing Lab.
All right, so we're going to be talking about stress distribution. So, all right, so when we talk about stress distribution, we have this equation right here that's going to be equal to minus 2, that's
Poisson's ratio.
Poisson's ratio, right? Plus 1 minus 2 Poisson's ratio, okay? And then that's all multiplied by B over A plus B, all right? So, and then we're multiplying the maximum pressure, okay?
So what's the maximum pressure?
All right, so B max is equal to 124,921 PSI.
Okay. And then we gotta solve for
So
sigma
you
x.
just plug all this back into here. So go ahead. What is this equal? Take my slide rule out here. Done.
So I'm doing that. You did that all with that?